Here we're looking at some probability problems that are a bit more complicated and have quite surprising, unintuitive answers. A lot of probability problems seem simple at first and then in the end turn out to have very unexpected answers, which I think makes them more interesting, but it means you do have to think a lot harder when you're working on them. So I'm going to show you 3 problems now, and for each one I recommend you look at the problem, listen to me explain what it is, pause the video, and at least think about what you think the answer might be. Just come up with an intuitive guess, or maybe try and work it out, and then see if the answer was what you were expecting. Certainly on one of the problems, you'll perhaps find the answer isn't what you thought it was going to be. Then there's going to be some other problems that have a similar theme to them that you'll want to try and do, and send me your answer to those, and we'll see the answers to those together next week. So the first one is in front of you now. A biologist is studying genes, A and B, that correlate with heart disease in rats. So 10% of the rats have gene A, 12% of them have gene B, and this is crucial here. The biologist finds that the incidence, so the occurrence of the genes, they're not mutually exclusive, they're not independent, which means they can happen together and one of them might affect the other one. So because they're not independent, having one of the genes makes you more, or maybe less, likely to have the other one. They're not unrelated. And also 3% have both. What is the probability that a rat would have at least one of the genes that correlates with heart disease? So perhaps pause and have a think what the answer might be. I know for a fact very few of you will have paused there, because no one ever does, but I recommend doing it. Anyway, let's look at what the answer is. So because they're not independent and mutually exclusive, we can't use some of the rules for multiplying probabilities and tree diagrams that we saw before. It would be wrong to say, well, it's a 10% chance of getting A, so if we make that, let's just do that as a 0.1, and then it's a 12% chance of getting B. If we did this calculation to try and work out the chance of getting A and B, that's wrong, because that's assuming that these two are independent. So you've got A and then B, and B is going to be 12%. But it might not be 12%, because if you've got A, the chance of getting B is different, because they're not independent. One might change based on the other one occurring. And because they're not mutually exclusive, you can't just add them together. You can't say, well, let's do 0.1 plus 0.12, because there might be some rats that have both of them. You might be counting the same rat twice. There could be a rat that's in this group and he's in this group. So therefore, if you add them together, it's like you're treating them as separate groups, but actually there's overlap between them. So the overlap there is the key word that's going to give us a clue on how to work this one out. A Venn diagram. So kind of starts off as you'd expect. We're going to have circle for gene A, and then circle for gene B. I would do the box on the outside as well, but there's no rats that don't have either. At least they're not mentioned just yet, so I'm not going to do that, but normally you'd have a box around the edge. So, okay, I'll do it wrong first. Again, the first thing you read is that 10% have gene A. So you might think, well, let's put 10 here, because 10% have gene A, 12% have gene B, oh, and 3% have both. So we put a 3 in the middle. The problem, perhaps now, is obvious. How many rats on this diagram have gene A? 13%. A is this whole circle, including the 3. But it says only 10% have gene A. So this is wrong. What I should have done instead, and what you should always do on these kind of Venn diagram questions where you have to fill in the Venn diagram is, that's terrible, isn't it? Where you have to fill in the Venn diagram, you have to start, if at all possible, at the center, in the intersection. Because that's the bit that must be right. 3% have both genes. Well, there's nothing that's going to change that. Nothing that's going to affect that. That 3% is definitely going to be in there. Now we say 10% have gene A. Well, in total 10 do. That means we need another 7 to go there. And in the case of B, another 9 go there. And you could work out what's on the outside as well from here, because it adds up to 100. But we're actually asked here, what's the probability that a rat would have at least one of the genes Well, that's these 7%, these 3, and these 9. So I'm just adding these up. That would be called the union, by the way. Adding everything in the circles up. And that's going to be 19%. So that's the answer to this question. So the point there is it's not just a case of adding up the 10 and the 12, or adding the 10, the 12, and the 3. You have to think about the potential for people, or in this case rats, being in both groups. That's a big theme that you'll see in some of the questions later. On to the next question. That involves some more props. And I'm somewhat limited, as you know, but we have today 2 bowls and some cutlery. So this is going to be a kind of standard tree diagram question with 2 events, but I'm going to ask a different sort of question to what you might be used to. So in this case, I've got 2 bowls to choose from. I've got the blue one, I've got the white one, and then within the 2 bowls are a different number of knives and forks. We've got 3 knives and 1 fork, and we've got 2 forks and 1 knife. This one even says knife, which is helpful. So the question is, on here, if I have chosen a fork, what's the probability that I chose it from here? So I'll say that again. If I chose a fork, what is the probability that I chose it from this blue bowl? So have a think. You might come up with a few kind of intuitive guesses. Maybe you're thinking 1 out of 3 because there's 1 fork here and 2 here. So there's 1 out of 3 forks are in this bowl. But that would be wrong. You might be thinking something along the lines of, or maybe it's 1 out of 7 because there's 7 pieces of cutlery in total and there's 1 fork here. Also wrong. Maybe thinking, I don't know, maybe you're thinking something like 3 out of 7 because there's 3 forks out of 7. But again, not true. The problem with this question is there's 2 events you have to consider. You have to consider one thing happening and then another thing happening and combine them and work backwards. So quite a lot going on there. The 2 events are firstly choosing the bowl. So I've got a 50-50 chance there, and then once you've chosen the bowl, choosing the knife or the fork. So we'll model this with a tree diagram, and then we'll see if we can answer the question. So let's come to here. I'll need this one on some paper. So it's a pretty easy diagram to make, actually. I don't think I have any problem with this one, but let's just do it together now. So the first choice is between the blue and the white bowl. So I'll put blue bowl there, white bowl there, and I've got no preference here. 50-50 chance, 1/2, 1/2. So far, so good. Now, this is a conditional probability question. The chance of choosing a knife and a fork is entirely dependent on whether you chose the blue or the white bowl. So if you chose the blue bowl, you've got a knife and fork choice. I'll put fork there and knife there. And the fork is 1 out of 4, and the knife is 3 out of 4. In the blue bowl. Choose the white bowl. You've got same 2 choices. You've got fork and knife, but they're different. If you came down here and chose the white bowl, in fact, you've got looks like 2 forks out of 3, and you've got 1 knife out of 3. Okay, so this is pretty straightforward diagram, I suppose. If we now work out all the different outcomes, this is a good thing to do in most tree diagram situations, because then you can very quickly decide what you want to do afterwards and you're not going to miss anything out. So blue bowl fork, you're going to multiply that and that together, 1/8. Blue bowl knife, same thing, 3 out of 8, maybe just timesing the top 2 together, 3 and 1, and then bottom 2 together, 2 and 4. This is using the AND rule, blue bowl and knife, 3 out of 8. White bowl and fork, we're going to get 2 out of 6. White bowl knife, 1 out of 6. Good check is to make sure that everything you've got adds up to 1, because the total has to add up to 1. There's a 100% chance of something happening. So this or this or this or this should be 1. And you can see it's going to be, because 1/8, 3/8 is going to be 4/8, that's a half. 2, 6, 1, 6 is 3, 6, that's a half. Half and a half is 1. So that's all good. Let me remind you of the question though. And let me actually phrase it in a very specific way here. So what you'll see written quite often is the phrase, given that. This means something has already happened. So given that I chose a fork, let's write this in here. Given that I chose a fork, so I've definitely got a fork. We don't know where it came from, but I've definitely got that. Any outcome that does not involve having a fork is impossible now. The only things that can happen are things that result in getting a fork. So in a moment, we're going to eliminate anything that doesn't have a fork in it because of this phrase, given that I chose a fork. Given that I chose a fork, and what I'm actually asking is, what is the probability that I chose the blue bowl? But the thing I want to highlight here is this given that phrase. Okay, so given that I chose a fork, well, that means that blue bowl and knife did not happen. That's impossible now. So forget that. Not involved. This is not in our world. White bowl and knife also not possible. They do not exist as far as we're concerned now. We don't care about those. They can't possibly have happened because of this. Now, these are the two things that could have happened. So these two now represent our denominator. Any calculation we do is going to be out of these. And the thing we're looking for is the blue bowl. So that's this one here out of the total of these two. So if I go to the whiteboard and actually do this calculation, we've got the 1/8. That's the blue bowl and fork. Out of, so there's another fraction here, fractions in fractions, out of the total of these two. So that's going to be 1/8 plus 2/6. So that's the calculation. Now, it looks a little bit intimidating, but it really is just adding some fractions and dividing some fractions. So we'll work through that. You could type in the calculator and it will give you the answer. If you've got a calculator, fine, you can use it, but it's good to know that you can do this without one as well. So let's have a look at that. Add these up together first. Well, initially I'm going to notice that 2/6 really is just 1/3, isn't it? So if we write that as this, to add two fractions, I have to have the same denominator. So I'm going to multiply this by 3 and this by 8 and get myself 3 out of 24 plus 8 out of 24, and then add the two top numbers together for 11 out of 24. So that's the sum there. So I'll put that in up here. So 1/8 out of 11/24. That might look odd, but remember, these are just numbers. That is just a decimal number, and so is that. So that doesn't look so weird when you think about it like that. But a fraction in a fraction can look a bit odd. Another way to think about this is that a fraction line there means divide. So really what we're doing is we're doing this fraction divided by this fraction, which is something that we can do easily if we can remember the method for dividing fractions, which we'll remind ourselves of now. So 1/8 divided by 11/24. So the method is you make it into a multiplication of the reciprocal. Stick with this one, kiss, which means turn into an x, to a times, flip, stick, kiss, flip, or multiply by the reciprocal if you're a bit more grown up. Another little trick here is that because these two are going to be combined in the same fraction, you're going to times the top and times the bottom, you can do cancelling out across the fraction before you actually do that. So because 24 and 8 can both be divided by 8, you can do that cancelling now. I'll just show you why that is. So it's going to become 1 times 24 on the top, and on the bottom it's going to become 8 times 11. Well, they're in the same fraction. You can divide that and that by 8, so you end up with, well, 1 times 3 over 1 times 11, which is pretty easy. It's that. And that's the final answer. So going back to the original question, given that I chose a fork, let's look at the bowls again. Given that I chose a fork, what was the probability that I chose it from this bowl? 3 out of 11 is the answer. Not intuitive. It's very hard for me to see a way that you could guess that just by looking at the situation. It's because you're calculating two events, and combining two events is quite a complicated mathematical process, as you've seen, but you've got to go through that process to get the right answer. So, on to the last one, which is perhaps the most unintuitive of the lot, but I think also the most interesting as well. I put this one over the Easter holidays, so some of you have had a go, and actually I did see some correct answers. So some of you are already aware of how this works, but most of the answers I received, unsurprisingly, were not right. But I don't blame you, because it is not an obvious question at all. Very relevant for the situation now. You'll have heard, if you've been watching the news, stuff about trying to find a test for the virus. People thinking we need to get more tests out, but it's a very complicated thing. Firstly, to make a test, but also to make a test that is accurate enough to be useful. Look at this situation here. A disease test is 99% accurate, so pretty good, right? I mean, you can't get a lot better than that. And in fact, most tests are not anywhere near this accurate. This is quite unrealistically accurate for a test for a virus. If you have the disease, you'll test positive 99% of the time. Sounds pretty good. If you don't have the disease, you'll test negative 99% of the time. Also sounds pretty good. The thing here is that sometimes if you don't have it, you can still get a positive test because the test just isn't very accurate. In this situation, 1% of all people have the disease. So in the country, 1 out of 100 people have it. And that's probably about right for the situation we're in, actually. And you test positive. So you've gone to the doctor, you've had the test, the doctor says, yep, you're testing positive, but what is the probability that you actually do have the disease? Again, you might want to stop, pause, think about what it could be. What does your intuition tell you? Probably tells you that you've got a pretty good chance of having it. It's a 99% accurate test, right? So you'd think I've got a 99% chance of having the test, having the disease if I've tested positive. Unfortunately not, though. And let's see why that is with some calculations. So a tree diagram, again, is a good model for this problem. So there's two events going on here. The first event is whether you have the disease or not, and the second event is whether you test positive or not. So let's try and put those onto the diagram. I think I'll go with this pen here. Yeah, okay. So first event, do you have the disease or not? Let's call this disease D, and not disease is not D there. Well, the disease is present in 1% of people, so you've actually got a chance of 1 in 100 of having it. I mean, it's pretty high, actually. If you think there's 65 million people in the country, that's 650,000 people, so it's not a small number, really. But 99% chance of not having the disease. If you have the disease, and this is all where the non-independence comes in, you get a different probability on the second set of branches, depending on what happened in the first one. If you have the disease, you have a 99% chance, or put P for positive, test here. But if you have the disease, unfortunately, you've still got a 1 out of 100 chance of getting a negative result. You wouldn't want that, would you? You've got the disease, you go for the test, they say, no, you're fine. That will happen in 1 in 100 cases. And that is, unfortunately, it's quite realistic for disease tests. If you don't have the disease and you get a test, there is still a 1 in 100 chance that you will get a false positive. They'll say you've got it when you don't. And thankfully, there's a pretty good chance, 99% chance of being told you don't have it when indeed you do not. So this tree diagram models the situation that we were describing in the question. Now, this is actually a given that question. It doesn't use the phrase given that here, but we could actually insert it, couldn't we? It says, you test positive. Well, that's a given that. Given that you test positive, what's the probability you actually have the disease? This question is the same as the knives, forks, and bowls question in its structure. So given that you have the disease, given that you test positive, that means that we're dealing with this and this scenario. This scenario and this scenario are impossible because you did not test negative. We can work these out now, just put them on. So disease and positive, that's 99 out of 10,000. Disease and negative is 1 out of 10,000. Not disease and positive is also 99 out of 10,000. And then these two, what is 99 times 99? For sure, you all know that answer. I'm going to use a calculator. Okay, it's that. Okay. So, overwhelmingly, most people here, but because we're saying we did test positive, get rid of that. And get rid of that. Our whole world is now just these two events. These are the only two things that can possibly happen in this question, because we're saying we did test positive, given that we tested positive. So given that you're dealing with these two events, what's the probability that you actually have the disease? It's like saying, what's the probability you actually came down here rather than came through here? Well, maybe you can see just by looking at the numbers, they're exactly the same. You've got just as much chance of having come down here as having come up here. You've got just as much chance of being part of the big group of people who have a small chance of a positive test as being part of the small group of people that have a big chance of positive test. We can put this into the same sort of fractions we used in the last question. So we're saying, what's the chance of this thing out of the total of the two? I'm not going to go through and work out the whole fraction question. It wouldn't be too difficult though. So what's the chance of that out of the total, which is just these two things added together? But without even working it out, hopefully you can see this was just going to be 1 out of 2, because they're all the same thing. It's one of these things out of two of them. So that's all going to simplify down in the end, if we worked it all out, to that. Which is a surprise. I think so anyway. It's also not a very pleasant surprise, because it means even in this super accurate test situation, half of the people who test positive don't even have the disease. It's not really a very good test. If you've got a disease that is only infecting 1% of the population, it needs to be a lot more accurate in order to find cases, because you're going to have way more people that don't really have it that nevertheless get a false positive. And we can see that using the tree diagram and the given that maths we use there. Okay, so have a look at the other problems that are posted. I would like to send the answers to any of them. You might not get them all, but maybe send half the answers if you can get those. They're all pretty tricky, I think, but also all quite interesting applications of this probability. Looking forward to seeing those.